All right, so this is Lesley Ott. She's a meteorologist from the NASA Goddard Space Flight Center, and she's going to be giving an overview of the carbon cycle. Yeah, and go ahead.
All right. All right, thanks. So yeah, as Ryan mentioned, I'm from Goddard Space Flight Center, and I want to say thanks again for organizing the workshop, to everybody who contributed, and to Caltech and KISS for organizing. This is really exciting, and as Ryan mentioned, there's a lot of exciting opportunities, so it's a very timely thing to be gathered and to be talking about. Just to give you a little background about me, for people who don't know me, I work at Goddard Space Flight Center. I'm actually an atmospheric modeler, so I focus on the atmospheric side of the carbon cycle, as well as atmospheric composition and things like air quality and atmospheric pollution. I work in a group called the Global Modeling and Assimilation Office, so we focus on global models of weather and chemistry and all kinds of Earth system interactions, which is why we're very interested in the carbon cycle, because it's an important part of how the Earth system functions. So just to get started, probably most of you have seen this figure. If you haven't, you'll see it again at some point. Everybody has to show it, but this is from the latest IPCC report. And this is basically summarizing radiative forcing changes from 1750 to 2011. So when I say radiative forcing, that's essentially a measure of how much radiation is being trapped in the atmosphere by different perturbations. So this is listing the different perturbations, trace gases, also aerosols and clouds, and in ranking those in terms of their impact. And this is just showing you that very clearly CO2 and methane are the top two radiative forcing agents that are influencing climate change. The IPCC report also found that we have about 0.86 degree Celsius increase in global mean temperatures over the that 1750 to 2011 period. That averages out to about 1.5 degrees Fahrenheit. We're also seeing, along with that, sea level rise and loss of glaciers, loss of sea ice. So a lot of changes in the Earth system in response to climate change, and we can see here that CO2 and methane, carbon gases, are the primary agents responsible for that. So we know that CO2 is increasing in the atmosphere, and it actually doesn't take a whole lot to know just that. We can learn a lot by just one observing site in Mauna Loa. So this is the Mauna Loa CO2 record. This goes back to 1957 and continues today, operated by NOAA and by partners. And what you're seeing here is just the monthly mean time series, and so you're seeing both the seasonal cycle of CO2, and you're seeing the black line is just sort of the annual mean, which is continuing to increase. And from just the surface observation, we can also get a sense of how much CO2 is increasing in the atmosphere, and that gives us a rough estimate of how much the total mass of CO2 that's being added to the atmosphere each year. So we have a good sense in the global scale of how much CO2 is being added to the atmosphere, and obviously that's really important for understanding climate change. To go into the bigger picture of the whole carbon cycle, not just the atmospheric part, this is put together by the Global Carbon Project, and they do a great job of synthesizing a lot of information that's out there about the carbon cycle into very nice, easy to understand materials. And so this is just telling you annual mean budgets of the carbon cycle. So the main thing that's driving increases is you have emissions from fossil fuel combustion, from cement productions. That's about 33 gigatons of CO2 per year emitted from those sources. About half of that stays in the atmosphere. So the other half is going somewhere. It's actually going into the natural land and ocean sinks. So the land and ocean are essentially doing us a huge favor all the time, because were they not taking up that extra carbon, we would have carbon, CO2 and methane building up in the atmosphere more quickly, and climate change likely progressing more rapidly than we've seen. So this interaction between the atmosphere and the land sinks and the ocean sinks is incredibly important. And at a global scale, we kind of get what these numbers are. We think we do. To show you how they do this, just a little more detail, this is showing you time series from 1750 to present. of the different breakdowns of carbon. So the top plots are the carbon that's being emitted to the atmosphere, essentially released from the Earth system. So the gray is fossil fuel and cement production emissions. The brownish part here is the effective change of land use, so that carbon being released to the atmosphere. And then these are essentially where that carbon is ending up. So we're seeing, we can measure the atmospheric increase pretty well from surface observations. We also feel like we understand the ocean sink pretty well, or at least a lot of people think they understand it pretty well. I'll go back to that. And so the way that this carbon budget is done is to basically add up the atmospheric increase, add up what the ocean models are telling us they're taking out of the atmosphere, and then calculating the land sink as this residual. You can see there's a lot of noise, there's a lot of interannual variability and a lot of things going on in this land sink. And we don't understand that nearly as well as we would like to. So what I've just showed you or tried to show you is that atmospheric CO2 is really important, and we kind of understand it at a global scale, but maybe not at a regional or process level. So this is just giving you a sense of some of the uncertainty in land carbon flux. This is from a study called MISTIMEP, which was an intercomparison of a lot of different land models, looking at a lot of different variables and processes that they're computing in trying to estimate land carbon flux. And we're just looking at a couple different quantities. So this is gross primary production, this is total soil carbon, and total living biomass. So gross primary production is essentially just an integrated estimate of the energy that's being taken up by biomass. And these are zonal means. So you're seeing the equator here. And one of the things you see is that there's a huge range of models in all of these processes. So even though we kind of have a sense of the global scale carbon budget, when you start looking at processes, when you start looking at how much biomass is being taken up by vegetation, when you start looking at where that's stored, if that's being stored in soil or in living biomass, the models disagree considerably. So this is a problem because not only do we need to understand what's going on today, we really want to be able to predict the trajectory of the carbon cycle in the future, particularly over the coming centuries. So the understanding of our processes is a limiting factor in our ability to model and predict the trajectory of the carbon cycle. Now, we know there's a lot of uncertainty in the land carbon flux. I don't think anyone in this room would disagree with me, but there's also some suggestions that we don't understand the other components of the carbon cycle as well as we should or as well as we would like to. So the ocean, to look at the ocean is something we think we understand pretty well in terms of carbon flux. And that's why we use it in those carbon budgets as kind of a quantity that we understand, and we'll subtract that off and we'll get the land sink. One of the reasons we think we understand the ocean flux of carbon is because of this very nice climatology of CO2 flux. And this was created by Takahashi, who basically used 3 million samples from ships from 37 years to look at PCO2, which is the mixing ratio of CO2 in the ocean, and compare that to the atmospheric CO2 mixing ratio to calculate flux. And so he used that to create this gridded climatology that's very widely used in the carbon cycle community. It's a great product, but when you actually start to look at the data that he had available to construct that, you start to see some holes. So these are the number of months with observations in that climatology. And so you see places where you have ships going back and forth, where there's a lot of ship traffic. You do a pretty good job of sampling the seasonal cycle, the shipping routes between Asia and North America and Europe. But in the southern hemisphere, we have a lot less ship traffic. Things get a lot less covered. There's regions where we don't have any observations. And in the Southern Ocean, which we know is a place that takes up a lot of carbon, that climatology might be based on just a few months of data throughout the year. So that also makes it hard for us to understand the processes that are going on in the ocean that are storing carbon. And what about fossil fuel emissions? Fossil fuels are something that we think we understand the best, right? So fossil fuels involve money, so people tend to keep track of them, unlike trees in the ocean and things like that. This is a plot of time series of emissions from 1960 to close to present for the 4 main carbon emitting regions. So you can see the US and Europe, we've been emitting a lot of carbon for a long time. Europe has gone down a bit, the US is kind of increasing or fairly stable. But the really noteworthy thing is the amount of carbon that's now being emitted by developing countries and rapidly developing countries, particularly China. So this is a really striking figure. When we think about uncertainty in fossil fuel emissions, uncertainty from developed countries is fairly low, again, because we have good records, we keep good track of things. In developing economies, there's much higher uncertainties, maybe 10, 20%. So as that trajectory continues, as developing countries make up an increasing portion of the world's fossil fuel emissions, so too does the uncertainty in global fossil fuel emissions. So it's not just that we don't understand the land carbon cycle, we really have a lot of questions about the whole carbon cycle and how all of those pieces are interacting. And that's making it very difficult for us to model and to predict. So this is a much less nice way of showing this than Ryan showed. Why are we in this mess? Can we measure fluxes directly? Yeah, we can. We can put up flux towers, and this is just a picture of what a flux tower looks like, because I think it's kind of interesting. So there are actually towers that are, placed throughout the world in forested areas. But when you look at this map, you can see that there are places with a lot of flux towers, but there are also places that have a lot of vegetation and not a lot of flux towers. And that makes it really difficult because the flux that a tower is measuring tends to be very localized, and it's very difficult to scale that up to regional or global fluxes. So these are really valuable in helping us explore processes at site levels and over small areas, but it doesn't quite give us everything that we need to understand the global carbon picture. So what do we do then? Well, one of the things that we're sort of forced to rely on is let's look at atmospheric CO2 measurements and let's try to infer fluxes based on those, right? Because the CO2 from the land is being emitted into the atmosphere. Let's use that information. So that's the primary method for that is called a CO2 inversion. And the way that this works, very simply, is to assume a distribution of fluxes. We know it's not going to be right, but we're trying to correct for it. So we assume some fluxes, we combine those with an atmospheric transport model, so we have some realistic winds, they blow the fluxes around, and then we combine those with observations. So we say, how well did my model with this prior flux guess match the observations? This is just showing you surface observations. You could use satellites, and increasingly people are using satellites for this observation step. And then this inverse procedure, which is nicely hiding a lot of mathematical equations, is basically tracking back the difference between your simulated CO2 and your observed CO2 and correcting the fluxes accordingly. So that seems like a pretty good idea, and it is a good idea. It's a very important technique for understanding the carbon cycle, but it's challenging for a couple of reasons. Basically, the observations that we're limited by, and the transport models and the nature of the CO2 distributions. So just to show that, I'm going to show a movie. This is from our atmospheric model, GEOS 5, and this is run at very high resolution. So it's a very nice, pretty view of atmospheric CO2. And basically what you're looking at is column CO2 mixing ratios. So these are the types of mixing ratios that are observed by satellites like GOSAT and OCO2. So it's a column mixing ratio. The satellite is looking down and seeing all of the CO2 molecules in a column. And
What resolution is this?
this is a 7-kilometer global. So it's kind of state of the art in terms of resolution for a global model. And it's not typical of most of the models that are used for inversions, but this gives you, we call it the nature run because it kind of gives you a view of what the nature of the atmosphere would be like. So a couple things I want to note with this. One is that we're looking at CO2, but it doesn't really look like a distribution of sources and sinks. We do see LA. LA keeps popping up here. And we do see fires. We see some fires pop out. But what you really see a lot in this distribution is weather. So these swirly things, these fronts, this is the weather transporting and mixing and doing a lot of fun things that complicate our jobs. So one of the difficult parts of the inversions is that, yes, we're relying on CO2 observations, but we can't always see directly the fluxes that we want to see. So we have to use a lot of information from the atmospheric transport model to be able to back out that flux distribution that we want to get to. This is also, you're seeing this change with the seasons. So you're seeing the CO2 go from the winter, when we have plants releasing CO2 to the atmosphere. We have high CO2 in the northern hemisphere. During the summer, the plants wake up, they start drawing CO2 out of the atmosphere, and you see higher CO2 in the southern hemisphere. So you see very low CO2 during the season. And then as we transition to the fall, you're going to see that pick back up with CO2 in the northern hemisphere increasing. The other point I should make here is that it's a little hard for you to read the color scale, but this is the pretty version of the movie, which is about a 16 ppm gradient between the maximum and the minimum values. If I did a 0 to 400 color scale, everything would be a very boring, similar shade of red. So what this tells you is that satellites, when they go, the difference is that satellites are trying to see the difference between high CO2 in a plume and low CO2 just outside of a plume is actually typically on the order of a couple of parts per million. So that's less than 1%. So that tells you something about the accuracy and the precision that you need for a satellite measurement to even give you any kind of useful information. So this is an incredibly, not only is it an incredibly complex system, it's an incredibly hard measurement to try to make and deliver to the community in a form that's useful. So now I want to go back to the other part that's making inversions difficult, which is data. What do we have for atmospheric CO2 observations? So this is the surface network of CO2 observations. This is coordinated by NOAA and other international agencies. And the symbols are all just basically different types of observations. You can see in certain places in Europe and over North America, we have a lot of observations, which is good, and that's really helpful for understanding the carbon cycle. But there's a whole lot of the Earth that we really care about that has a lot of vegetation, a lot of things going on, that we don't have a lot of observations for the surface. So particularly northern hemisphere high latitudes, we have a lot of biomass there and a lot of potential changes with permafrost thawing and very little coverage in terms of surface observations. The tropics as well, the rainforest over South America, there's a ton of biomass there, and we really don't have a lot of ground truth of what we think is going on in terms of the ground-based in situ network. So that sort of opens the door for let's sense CO2 from space. I mentioned before that it's challenging because we're looking at really small gradients in atmospheric CO2, but you got to start somewhere. So I'm going to go through the sort of history of atmospheric CO2 remote sensing. And you know, it's definitely a work in progress, and there's been some progress, but there needs to be more. So first we had AIRS, and I think AIRS launched in forget if it was 2001, 2003. But one of the nice things about AIRS is that we have a long time series of AIRS. AIRS is a little bit different measurement than the movie that I showed. AIRS is actually sensitive primarily in the mid-troposphere, so it has very little sensitivity near the surface. And AIRS was an instrument that was primarily designed to deliver temperature and moisture profiles. So the fact that we're getting CO2 out of it all is really incredible and innovative, because this was sort of not the main thrust or the reason this instrument was designed. So this is just showing you through the year, the seasonal cycle of CO2 that's observed by AIRS for January, April, July, and October. And the AIRS data haven't been used widely for some of these flux inversions, in part because there's a decent amount of scatter in the data. You can see some evidence of it here. And there's also some kind of strange artifacts, like a band of CO2 in the southern hemisphere that there's some debate about whether or not that's an artifact of the remote sensing, or is there some physical mechanism. This doesn't really fit with some other observation types, so there's some debate about, you know, the quality of the data in places like this. So again, a really nice record and something that gives us a nice view of the global carbon picture and total, maybe global mean CO2 in the mid-troposphere, but it's not really giving us what we need to be able to infer fluxes. So the next instrument we had to work with was SCIAMACHI, which was launched again, I think, early 2000s, and this was on the European ENVISAT. And this was, again, among the first space-based CO2 measurements. And we did learn some things. We learned some things about the spatial distribution of CO2. And again, you can see, seasonal cycle of CO2 and increases being observed by the satellite. But SCIAMACHI also had a lot of scatter. There were several systematic biases, which were noted by multiple studies as a big impediment to flux inference. So that was sort of the predecessor to the GOSAT mission. It's a similar technology. GOSAT launched successfully in 2009, and it's a technique very similar to OCO2, which measures spectra in reflected sunlight. And again, this is looking at just 1 year of GOSAT data for different months. So GOSAT was a big improvement in terms of bias, in terms of data quality, but you'll notice that there's still some big places that even with GOSAT we didn't have data. The Amazon, which I mentioned, we have a lot of biomass. We really want to understand what's going on with the carbon cycle there, and it's kind of a black hole for GOSAT. Also the high latitudes, you'll notice that during summer you've got some observations of CO2 from GOSAT, but during winter months, when it's dark, GOSAT can't see because it needs that reflected sunlight. So in some of these places where we really want to understand the seasonal cycle and how that might be changing, we're limited by the fact that we only have observational coverage during certain months of the year. So this is a big advancement still, but it hasn't really answered all of our flux questions, in part because of the sparse coverage and also because there were small systematic biases. This was an interesting lesson that was learned from GOSAT, was there was a very small systematic bias between the land and ocean in one of the versions of the data. And this was tiny. This was probably like 0.1%, the kind of error that you would like to ignore and say that doesn't matter. But because these inversion techniques are inferring large flux corrections based on very small gradients of atmospheric CO2, even a small bias in the land and ocean data can give you a big error in your flux attribution. So that was an important lesson that was learned from GOSAT and still, I think, a work in progress. So now, after GOSAT, GOSAT's still going, but we now have OCO2. OCO2 launched successfully in July of 2014. So we're now looking at basically the first full year of data. And in terms of flux inversions and what's going to come out of that, that's still an open question. I think it's going to answer a lot of questions, but we don't know. You basically need 1 year of data to do the flux inversion and really understand what's going on with the seasonal cycle. And we're just now getting that. So stay tuned. In probably 6 months, you're going to start seeing a lot of papers discussing the flux inversion results. But for now, we can look at the data and we can get a sense of what it looks like. So this is a movie that Dave Crisp gave me, and this just shows XCO2, which is the column CO2 amount that OCO2 is observing from May through July of 2015. And so you get to see the way that OCO2 observes the world. And one thing to note is we have much better coverage than GOSAT over the oceans. So very encouraging that we're going to be able to understand ocean flux a little bit better from OCO2. We also have some nice coverage over the land. And this period is particularly nice because you see the stark transition of spring drawdown. The plants sort of come to life, start drawing CO2 out of the atmosphere very rapidly. And OCO2 does a really beautiful job of capturing this. And hopefully you'll hear a little bit more about that later today. So these observations are really, really exciting and giving us some hope that we finally have a satellite data set that can help us understand not just the atmospheric CO2 distributions, but some of the processes underneath. And can we use that to evaluate models and how well they're performing? But again, to be continued because we don't have those flux inversion results back yet. So there's a lot of work left to do to understand the global carbon cycle. It's kind of shocking to me sometimes because it's such an important problem, and yet there are so many things we don't know. So that's either good news or bad news, depending on how much work you want to look forward to. I wanted to highlight just some of the big questions that are remaining for the carbon cycle, especially since we're going into a workshop, the things we have to think about. Why do bottom-up land models underestimate the land carbon sink? This is something we've been talking about for probably 15 years, but we still don't totally understand what's going on. There are some hints that maybe this is CO2 fertilization effect being, which is basically the impact of rising atmospheric CO2 levels on vegetation, and that not being fully accounted for in land models. But there's active debate about that, and we really don't understand it very well. What are the relative magnitudes of sinks in North America and the tropics? For a long time, we did some inversion studies, and the model seemed to indicate that North America, mid-latitudes of North America, was the main place that was responsible for drawing CO2 out of the atmosphere. And now there's a growing body of evidence and work that's suggesting maybe some of this is going into the tropics. But again, we really aren't sure. We don't know the processes, the how, when, why, where, of where this flux is going. And how, most importantly probably, how is land carbon flux going to change in the future? As I mentioned, the land and the ocean are each taking up about 25% of the emitted CO2. So we really, if you don't want the world to get warmer, you should really hope that that continues. And we need to understand the processes a lot more to know if that will or if things are going to go in the wrong direction. So just to highlight a couple of the open questions and places where we are going to need to do better observationally. This is just an assessment, a paper that was assessing soil carbon contained in permafrost. And essentially, you don't have to pay too much attention to the numbers, but essentially their estimate of the amount of carbon that's contained in permafrost soils is that there's about twice the amount of carbon in the permafrost soil compared to what's been released and emitted into the atmosphere. So there's a huge amount of carbon that has basically been immobilized because it's trapped in frozen soil. As those soils warm and thaw, that carbon is becoming more vulnerable to being released to the atmosphere. And that could be a real game changer in terms of climate change, because that's the kind of feedback that can magnify the effect of our carbon emissions. And understanding this is a really tricky thing, because if you saw both the GOSAT, the OCO2 data, the surface networks, sensing either through in situ instruments or from satellites at high latitudes is very challenging. And so getting measurements of this, trying to understand these processes, is a big challenge going forward and something that we all have to think about. This is an example of carbon stocks in California for 2010, and this is showing carbon changes between 2010 and 2001. And basically, the brown areas here, a lot of this is indicating changes due to fires. So again, this is a big question for the carbon cycle going forward, and in terms of understanding carbon-climate interactions. As we have more droughts, as we have more of our carbon vulnerable to wildfires, what does that do to the atmospheric capacity, or to the atmospheric growth rate of carbon? What does it do for the land's capacity to reabsorb carbon? Again, it's an open question. It's something we need to think about when we're designing our next generation of satellite missions. So I will also say that since it's a land focused group, I didn't focus too much on ocean questions, but there's also big questions on the ocean and the anthropogenic emissions sides. So for the ocean, in particular, warming waters, ocean acidification, how are those affecting the ocean's ability to store and keep storing massive amounts of carbon? There's some indications that that is not something that can also continue indefinitely. And in terms of fossil fuels, again, I mentioned the changes in developing economies. We're also in an exciting time where people are actually talking about having some sort of a carbon treaty, an international carbon treaty, which would be really exciting. But it also brings to mind the challenge of how do you actually enforce that? How do you know if people are doing what they say they're doing? How do you keep people honest? Do we have the observations right now to be able to do that? I would say that we don't, but we could if we really thought about it. So all of these things led to this 2015 Carbon Climate System Workshop, which was held in Norman, Oklahoma last March. And this was essentially preparing for the pre-decadal process that Ryan shed some light on, which is a big process of NASA trying to decide what satellite missions and Earth system science priorities to tackle in the next 10 years. And so these were the 4 main recommendations that came out of that workshop. And there's a lot of text here, but I'm going to try to pick out the keywords that I think are really important. So the first one was developing and sustaining a time series of global atmospheric CO2, methane, and CO concentrations with sufficiently small and understood biases at spatial and temporal resolutions that allow rigorous evaluation and improvement of models to reduce uncertainty in future projections. So what's critical here, one, is sustaining a time series, because all of these satellites that we've had, this has all been great, but it's been a single mission. And really, in terms of understanding long-term climate changes, we need more. We need a continuous data record. We need something that helps tie those satellites together. And so this time series, this idea of having continuity, is a really, really important thing for atmospheric CO2 observations. It's something that we've had for ozone observations in the atmosphere, but for CO2, it's something that we're now beginning to tackle. This issue of biases is also a critical one. I mentioned that with the GOSAT data, that a very small bias can wreak havoc in flux estimation. So we need to really design measurements that have small biases and to try to understand the biases in the observations that we have. The next one was improving attribution and quantification of patterns of carbon emissions, thereby reducing the growing uncertainty of anthropogenic emissions of carbon, which is, again, acknowledging that we need to understand the anthropogenic emissions better. And one important component of this is that in these inversion studies, they're actually often assuming that the anthropogenic emissions of carbon are perfectly known, which is not the case. So our ability to constrain anthropogenic emissions directly impacts our ability to estimate land fluxes using inversion techniques. The next one, acquiring the critical measurements that allow attribution of fluxes to specific mechanisms and processes within terrestrial and marine carbon cycles. Many of these measurements are expected to be priorities for disciplines such as terrestrial ecosystems, ocean biology, biogeochemistry, and climate. So this is basically saying we need to tie our carbon measurements to other types of observations so that we can really get at the processes, not just the atmospheric CO2 increases, but what are the processes that are driving this so that we can model them better. And this is kind of saying that we can't cover the full cost of this, so please, other programs chip in and build some satellites that'll complement the CO2 observations. Addressing how the natural dynamics of the carbon cycle and human activities feed back to influence future trajectory of the atmospheric carbon fraction. Again, this is talking about feedbacks and processes and understanding how those things are all functioning together. So what are we doing right now? This is my last slide. This is kind of the cliffhanger of what's going on right now. There are several different choices that we can make when we think about future space-based CO2 observations. We have a couple different techniques we could use. We could use passive systems. Those are like what we've used for OCO2 and GOSAT. Observations of near IR spectra and reflected sunlight. And those have advantages. We've done them before. We know how to do them well. But they have some disadvantages too. They're subject to biases by atmospheric scatterers like clouds and aerosols. You also need sunlight. So there's places like the polar night where you're not going to be able to make observations with a passive observation, with a passive technique. Active systems use a laser for illumination, so that's a different technique. That's never been deployed in space for CO2, so it's essentially a new technique that's been in development at NASA for a little while in preparation for the last decadal survey, which actually called out an active CO2 mission. That obviously hasn't happened. So there's still been a lot of active technology development going on, but that has some advantages in terms of being able to see at night, being able to get seasonal coverage of the high latitudes during winter, reduction in bias from clouds and aerosols, but probably a little bit more random error in that measurement. So it's a trade-off like everything. We also have to assess orbital options. So low Earth orbit. This gives you global coverage, but the observations are limited. So you might pass over a certain location every 16 days or so. Geostationary orbit, you give more frequent observations, but you don't get the global coverage. So again, what's the trade-off? How do you observe the problems and the processes that you need to understand better? And so how do we decide all that? This is a lot of money. These things are a lot of money. You don't want to bet on the wrong horse here. So right now, there's a lot of planning going on between modeling teams, which is what I do, and people who are developing instruments and trying to think about instrument formulations to define some experiments so that we can see how well we need to, different strategies will be able to observe and measure the processes and the techniques that we really want to go after. So that's what we're thinking about, and I'm happy to be here to talk more about it. Thanks.